This is the second video in a series devoted to differential equations, and today we're going to talk about so-called first-order linear differential equations. Now, last time we talked about a lot of the terms associated with differential equations, and so from the knowledge of those terms, you should be able to write down a general form for a first-order linear differential equation today. That being said, here today in this video, we're going to develop a general solution strategy for these types of differential equations. Okay, before we get into it, let's look at a proper definition. So we say a first order differential equation is linear if it can be written in the following form. And this follows immediately from those definitions we saw last time. So we have y prime plus a of x times y equals b of x, where a of x and b of x are some sorts of functions. And notice by first order, I mean the highest derivative I see is a first derivative, y prime. And by linear, I mean linear in the variables y and y prime. And that's exactly what I have here. A and B do not have to be linear functions. It's not talking about linearity with respect to the independent variable. Okay, so let's look at some quick examples and non-examples before we start solving these things. So here are three examples. Y prime plus 2x times y equals sine of x. Well, that's exactly in this form already. Then e to the x times y prime minus tangent of x times y equals 4x. And so that is not immediately in this form, but we can put it in this form by dividing everything by e to the x. And so that would maybe be put e to the x in the denominator here and an e to the minus x here. And then it is in that form, so we're good to go. Now let's look at this one. We have x squared plus 1 times y prime plus 3 sine of x equals x times y. Again, this is not immediately in this form, but we can transform it pretty easily. Notice we could have y prime minus x over x squared plus 1 times y equals negative 3 times sine of x. So in particular, in this setup, the role of our function a of x is being played by minus x over x squared plus 1, and the role of our function b of x is minus 3 times sine of x. So now let's look at a couple of non-examples. So maybe our first non-example would be y prime and then plus y squared equals 5 cotangent of x. So this is non-linear because we have this square. So it's not linear in our dependent variables and the derivatives. And then here's another one, y prime times y equals e to the x. Again, that's also non-linear because we've got a quadratic type term right here. Interestingly enough, something like this we'll be able to solve in the next video, whereas something like this is actually extremely tricky to solve. Now let's look at this one. We have e to the y plus y prime equals 0. Again, y is wrapped up in this exponential function that makes this nonlinear. Maybe another example would be something like y double prime minus y prime plus 3y equals 7. So that is linear, but it's not first order. So that's another example of a non-example, if you will. Okay, so now that we've got this taken care of, let's look at a couple of first examples before we develop our general problem-solving strategy for these types of differential equations. Okay, so here are two starter examples of first-order differential equations, first-order linear differential equations that we can solve maybe without a general strategy, just by sort of following our nose. So this first one is x times y prime plus y equals cosine of x. So maybe the best thing to notice immediately is that if we take the derivative with respect to x of x, we get 1. And then if we were to write that as x prime, then we see that there's actually an x prime snuck in right here. If we maybe take this plus and move it over, we see that we could just slide the number 1 in there and then envision 1 as x prime, the derivative of x with respect to itself. Okay, so that being said, we can take this differential equation and rewrite it as follows. So we have x times y prime plus x prime times y equals cosine of x. And I didn't just do that randomly. I did that because that's our actual general strategy for solving these types of differential equations, is to take this left-hand side and rewrite it so it looks like the product rule has been used. And that's exactly what we did here. Notice this looks like the product rule has been applied to the function x and the function y. Just keeping in mind that the derivative of x is 1 because that's our independent variable at the bottom. So that being said, we can take this left-hand side and instead of writing it as like this expanded product rule, write it as the derivative of x times y. And then notice if we take this derivative with the product rule, we end up with this immediately. So that's the trick here, is to somehow envision what's happening on the left here, or the left here more generally, as a product of a derivative of a product of functions. Okay, so anyway, so we've got x times y prime equals cosine of x. But now that we've got that, we have the derivative of something equals something else. This only has our kind of root variable, our independent variable there. So that means we can solve this differential equation by taking the antiderivative. So let's take the antiderivative of both sides with respect to x. The antiderivative and the derivative cancel each other, leaving us with x times y. And then the antiderivative of cosine is sine. So we have sine of x, but then we need plus a constant. So now finishing all this off, we have y equals sine of x plus some constant over x. And that would be like our most general solution to this differential equation. Okay, so again, I want to reiterate the fact that what we do is look at what we're starting with over here on the y side of our equation and try to envision it as a product or a derivative where the product rule has been used. Okay, so now let's see what we have over here. We have y prime plus y equals 2. So this one is not immediately so clear. It doesn't look like the product rule has really been applied here because we don't have anything multiplying out front. And in fact, we have the same coefficient in front of y prime and y. And that brings us to one of the most important tricks for solving differential equations, and that is multiplying by a so-called integrating factor. And that integrating factor should help us create this sort of setup that we had over here already. So what integrating factor should we multiply by? Well, we'll be able to find a formula for it in general, but before we do that, let's just look and notice we want to multiply by a function so that this left-hand side looks like the product rule has been applied, but that means the derivative of that function must be itself. And that motivates us to take this entire equation and multiply it by e to the x, because that's the unique function whose derivative is itself. Well, up to multiplication by a constant. Okay, so that's going to leave us with e to the x times y prime plus e to the x times y equals 2. But maybe we could take the second e to the x and write it as e to the x prime. Remember that the derivative of e to the x is e to the x, so that's legal. But just as we did here, we can envision this entire left-hand side as a product where the derivative has been taken with the product rule. And in fact, what we have here is e to the x times y prime equals 2 e to the x. I left off my e to the x when I multiplied through before. But now we can pretty much finish it off. We can take the antiderivative of both sides. That's going to leave us with e to the x times y equals 2 e to the x plus a constant. Then we can divide by e to the x. That leaves us with y is equal to 2 plus that constant times e to the minus x. And so that would be our final, most general solution in this case. Okay, so now let's maybe start to look at our general strategy. So our general solution strategy will use what I like to call the power of wishful thinking, which is really just hoping that this equation is a lot nicer than it might look. And so in our case, motivated by the examples that we saw, the question is, can we transform our arbitrary first order linear differential equation to one that looks like the derivative of something on the left-hand side equals something on the right-hand side, where I guess I should be careful to point out that this stuff on the right-hand side only has x's in it, whereas the thing on the left-hand side could have x's and y's. Okay, so motivated by our second example where we multiplied by something to make this occur, let's see if we can do that. So let's multiply our equation by something that we'll call alpha x. So this will be our integrating factor. So just to reiterate, we're taking alpha x and multiplying it out into our given equation. So that's going to make this thing look like alpha of x y prime plus alpha of x times a of x times y equals alpha of x times b of x. So notice we've got all x's on the right-hand side. So this left-hand side is the thing that we want to be the pure derivative of something. So in particular, what we want is for this left-hand side. So let's maybe color code this a little bit. So this left-hand side, which I've underlined in brown, we want that to be equal to alpha of x times y, all of that prime. You might say, well, how do I know that we want it to be equal to that? Well, if we look carefully at this first term, we see that we have alpha x by itself times y prime. And that's exactly what we would have like if we were taking the product rule with this, at least for one of those terms. Okay, so now let's expand this out. So just to reiterate, we want this product rule expanded to be the same thing as this brown underline. So in other words, what we need to happen is for alpha of x times y prime plus alpha prime of x times y to be equal to alpha of x times y prime plus alpha of x times a of x times y. We need something like that to happen. So again, let's color code this a little bit. So this is just that brown taken straight down. And then this thing right here is this product of alpha and y expanded out with the product rule. Okay, so now let's simplify this a little bit before we start doing some other calculations. So first of all, I'd like to notice I've got an alpha x y prime on both sides of the equation, so I can cancel those. So let's cancel that and that. And then furthermore, I've got a multiple of y on both sides of the equation, so we could divide by y. You might be a little bit worried here because what if y equals 0? You can't divide by y. But we're assuming that y is not identically the 0 function. So dividing by y gives us alpha prime of x equals alpha of x times capital A of x. So again, that's from dividing both sides by y. Okay, so now let's maybe bring that up and then we will finish off our general solution strategy before doing a couple of examples. So in the last board, we determined that if it's possible to multiply by a so-called integrating factor, and I mean multiply our entire differential equation by this integrating factor, that turns the left-hand side of this differential equation into something nice, then that integrating factor, which we called alpha, had to satisfy this differential equation. We have alpha prime of x equals alpha of x times a of x. And we'll solve this differential equation, this remaining differential equation for alpha, and we'll see that it's actually not so bad. So let's first maybe divide both sides by alpha. And that gives us alpha prime of x over alpha of x equals a of x. And then from there, we've got a derivative in the numerator of the given function in the denominator. And we think, oh, that looks like a logarithmic derivative has been taken. And in fact, that's exactly what happened. So notice that if we take the derivative with respect to x of the natural log of technically the absolute value of alpha of x, but I'll leave the absolute value out, it all kind of shakes up in the end with arbitrary constants. Then that gives us a of x. So let's just be very clear here. The derivative with respect to x of the natural log of alpha of x is this by the chain rule. But now we've got the derivative of something equals a of x. That means this something is the antiderivative of a of x. So last time we looked at careful and quick ways to write the antiderivative. We'll just use a quick way. So we've got the natural log of alpha of x equals the antiderivative of a of x. Again, I don't need to add a constant in here because that'll all shake up later. But now we want to solve for alpha, and we can do that by exponentiating both sides. And we have alpha of x equals e to the antiderivative of a of x dx. Sometimes that's written as exp, antiderivative of a of x dx. So things are looking fancy. We've got an antiderivative within an exponential function, so that's pretty cool. Okay, so now let's summarize that right here. So properly, we have alpha of x equals e to the antiderivative of a of x dx. Okay, so now that we've got that, we're ready to finish this general solution off. So we just did a bunch of work to figure out a formula for our integrating factor alpha, and it turned out that alpha of x was the exponential of the antiderivative of a of x. And as long as we set alpha equal to that, then this left-hand side, which is maybe what I would call the bad part of our first order linear differential equation, turns into something nice. Now we just have to solve this nice equation, which is given by the extreme left and right-hand side of this, which is our original equation after all of this stuff has been happening. Okay, so let's see. We've got alpha of x, y, quantity prime, in other words, the derivative of that product, is equal to alpha of x times b of x. But now we've got the simplest type of differential equation. We can take the antiderivative of both sides. That gives us alpha of x times y equals the antiderivative of alpha of x times b of x dx. Now I'm going to add my constant in. I didn't need to in the other cases because it could have just been absorbed into this final constant. But that allows us to solve for y. So we've got y is 1 over alpha of x times the quantity, the antiderivative of alpha of x times b of x dx plus a constant. The important thing is this 1 over alpha of x is multiplied into this antiderivative and the constant. It's easy to forget that it's multiplied into the constant. So that's our general solution along with the necessary integrating factor. So that allows us to kind of write something down over here. So let's do that. So we have a general solution, like I said. And that general solution, which we'll call y, is 1 over alpha of x times the quantity, the antiderivative of alpha of x times b of x dx, plus an arbitrary constant where that alpha of x is equal to the exponential of the antiderivative of a of x dx. So now, for better or worse, we have just like a formula to use to solve like any nice first order linear differential equation. And I guess I should say there's something important going on here with the interval that this solution holds in. And maybe I'll make a note of that right here. So this is valid. So this is sometimes called the interval of validity for any interval where a of x and b of x are continuous. So I'll write that, continuous. Great. So that's important to keep in mind as well. Sometimes you have to restrict the interval on which this is valid. Okay, so now let's jump into some examples. Hey everyone, I hope you're enjoying the video. I'd like to take a moment to ask you to subscribe. Subscribing is really the best way to support me in my mission to continue providing excellent math videos for everyone. Thanks, and now back to the video. Now we've got a general solution strategy. We're ready to apply it, a couple of times for practice by solving examples. Okay, so our first example will be y prime plus 2y equals x cubed times e to the minus 2x. Now, really quickly, notice our function a is just the number 2, and then our function b is this like polynomial times exponential function. I guess I should also point out that the interval of validity will be all real numbers. And that's because the a function and the b function are continuous on all real numbers. So that's cool. Now let's get to it. So let's first calculate our integrating factor. So alpha of x will be equal to e to the antiderivative of 2 dx. Again, given the fact that the 2 is playing the role of a with our general solution strategy. So that's going to be e to the 2x. Great. Now we can just write down the final solution. So our final solution will be equal to 1 over e to the 2x. I can write that as e to the minus 2x. And then the antiderivative of e to the 2x times x cubed e to the minus 2x. So that would be this alpha times b term. But notice that just cancels out the exponential and leaves me with my x cubed dx. And then I have plus a constant. Okay, well, let's maybe be a little bit more clear than that. This is my alpha of x times b of x. And here we're using the fact that e to the 2x times e to the minus 2x times x cubed is just equal to x cubed, because these two guys just multiply to the number 1. Okay, now we're ready to finish this thing off just by taking an antiderivative. We have e to the minus 2x. The antiderivative here will be 1/4 x to the 4th, and then we have plus a constant. Okay, and then here this is just going to be equal to, so let's see, 1/4 x to the 4th times e to the minus 2x plus a constant times e to the minus 2x. And that would be our final solution. So let's maybe bring that down and put a box around it. That's our final solution of this first example. Now let's do a couple more. So for our next example, we'll look at the differential equation y prime minus 1 over 2x plus 1y equals 1. So let's start by noticing that the function multiplying y is not continuous everywhere, so that means our interval of validity will just be broken up into intervals where this thing is continuous. But that thing will be continuous from minus infinity to minus 1/2, or from 1/2 to infinity. And the thing is when you solve a differential equation, you have to make a choice as to, do you want this differential equation to be solved over our first interval or our second interval? If you have an initial condition, then you can just like take whichever one contains the initial condition. Okay, so let's keep that in mind as we move forward, and maybe we'll solve it over this one. Okay, good. So let's first calculate our integrating factor. So we need our alpha of x, which is e to the antiderivative of a of x. So let's see, alpha of x, so that's going to be the exponential of the antiderivative of that, but that's going to be minus the antiderivative of 1 over 2x plus 1. We factored the minus sign out. Notice the minus sign is attached here because we have a plus built in right there. Okay, so let's see, that's going to be the exponential of minus 1/2 times the natural log of 2x plus 1. So something like that. And then the exponential and the natural log should cancel each other, but this minus half is like a little bit worrisome. Luckily, we can use logarithm rules and rewrite this as e to the natural log of 2x plus 1 to the negative 1/2 power. Bring that multiplier inside, and as we bring that multiplier inside, it becomes an exponent. Now the exponential and the logarithm can cancel, and that's going to leave us with 2x plus 1 to the negative 1/2, or in other words, 1 over the square root of 2x plus 1. And I guess I should be careful here and note that when I took my antiderivative, I did not have an absolute value there. And I didn't need an absolute value because we're working in the interval where this function is positive. Now notice if we were working in the interval where this function was negative, so let's maybe do a little bubble around that. then this thing right here would end up being something like the natural log of minus 2x minus 1. Because taking the absolute value of a negative number is just like negating it. Okay, so you have to be careful about that. Okay, so there's my alpha of x, and now I'm pretty much ready to write down my solution. So now I have y is equal to 1 over alpha. So that's going to be the square root of 2x plus 1. And then times the quantity, the antiderivative of alpha of x times b of x. Of alpha of x times b of x. So that's going to be 2x plus 1 to the negative half dx plus some constant. Now we have to take the antiderivative of this, which we can do using the power rule and really like the chain rule built in or whatever. I won't do that carefully, but what you end up with for the antiderivative of this is in fact just the square root of 2x plus 1. And we can check that just by taking the derivative, and notice that we get this exactly. The half and the 2 cancel. So this square root 2x plus 1 times this square root of 2x plus 1 will cancel, and that'll leave us with 2x plus 1 plus a constant times the square root of 2x plus 1. And that would be our final solution here. Okay, let's do one more. So our last example will be y prime plus tangent of x times y equals secant of x. So that's already set up in our format over here. I'd like to also point out that we've got an initial condition here, which is y evaluated at pi over 4 is 0. Next up, let's notice that tangent and secant are discontinuous at half integer multiples of pi over 2 because they both have cosine in the denominator. So that tells us that our interval of validity here will be minus pi over 2 to pi over 2. It's really kind of anything of that form, kind of shifted around the real number line by pi. We're choosing that one in particular because this is the one that includes the number for our initial value. Okay, so let's get to it. Okay, so we first need our integrating factor, alpha of x. So that's going to be exp, and then the antiderivative of the tangent of x dx. Let's do this out just so that we have a little bit of practice. So this is going to be the exp of the antiderivative of the sine of x over the cosine of x dx. And then let's recall that if we set u equal to the cosine of x, then du is minus sine of x dx. And that tells us that the integral of sine of x over cosine of x dx is in fact just minus the integral of du over u, which is minus the natural log of u. Okay, so that being said, in our specific setup, that'll end up with the exponential of minus the natural log of cosine of x. But the standard thing here is to take this minus sign, bring it in, and turn this into a secant. So we have the exponential of the natural log of secant, but that's going to, in the end, just give us secant x because the natural log and the exponential cancel each other. Now, you might be worried a little bit about the absolute value that we got rid of here, but on the interval from minus pi over 2 to pi over 2, the secant is always positive, so we didn't really need to worry about it. Okay, so there's our alpha of x, and now we're ready to just finish the whole thing off. So we have y equals 1 over of alpha, which is cosine, because 1 over cosine is secant, so 1 over secant is cosine. And then we have the antiderivative of alpha times b, that's secant times secant, which is secant squared x dx plus a constant. Let's recall that the antiderivative of secant squared is tangent. Then tangent times cosine is sine. So that means we have y equals the sine of x plus some constant times the cosine of x. Just to reiterate, that's what we get when we multiply this cosine through to both of these terms, keeping in mind the antiderivative of secant squared is tangent. Okay, so now I'm going to leave you with a couple of warm-up exercises. Okay, I've got 3 warm-up exercises. So for each of them, solve the differential equation and then give an interval of validity. So you might have a choice as to that, although your solution might look a little bit different based off of what we saw with taking natural log absolute values and stuff. So each of these is not quite written in this form, so you might have to do some manipulation first. So the first is x plus 1 times y prime plus y equals x squared plus x. And we have the initial condition y0 equals 3. Y evaluated at 0 is 3. Next, we've got x times y prime plus the quantity 1 plus x cotangent of x times y equals 0. So this is a so-called homogeneous differential equation because we've got 0 on one side and then everything with y's on the other side. Then finally, we have xy prime plus 2x squared plus 1 times y equals x cubed times e to the minus x squared. And that's a good place to stop.